so the last method for solving a system is the addition or the elimination method. Sometimes you'll see it called elimination because you're adding the two to eliminate a variable. So sometimes called addition, sometimes elimination. That means the same thing. We're going to add these two equations together such that one of the variables will fall out when you add. Well, this one's already set up for that, which isn't always true. We'll see that in the next example. But right now, I could add these equations together as they sit. X plus x is 2x. Y and minus y eliminates itself or adds out, equals 5 and 1, which is 6. And now you have an equation you can solve. Now listen, this doesn't work if something doesn't drop out. You have to eliminate a variable so it's then solvable with just one variable. So that worked well. X is 3, as we've known on this little example, that the solution is the point where they cross at 3, 2. So X is 3, and then its counterpart, its Y value, you have to take the 3 into one of these former equations. We don't have one of those nice little equations like we have with substitution, so we do have to go up into some just regular equation form. It doesn't matter which one you use. 3 plus Y equals 5. So Y equals, throwing the 3 across, would be 2. So it's counterpart 2. 3, comma 2, the solution to that system by addition. So no matter what method you're using, you should get the same result. All right, let's try that again. An addition problem, that is. So maybe another you try on that page. I lost my page, sorry. Okay, so let's say the third you try. It looks like this. And it's not as pretty as the examples we started with. I can't just see the solution or how to add those together. For one thing, this equation's jumbled up, so I need to write these in order, x, y, constant order. So throw the 2x over. And at least then I can compare the x's and y's. Now, if I were to add these two equations together as they stand, nothing would drop out. I'd get 2x's, 14y's. Nothing cancels out, and I wouldn't be able to solve it. So I need to do some groundwork, either eliminating the y's or eliminating the x's. The x's will be easier in this example because if I were to double this equation, completely allowed to do that, as long as you do it all the way through, you can do anything you want to an equation. So I could double every number in that equation and then add them together, and then the 4 x's would cancel. They're already different sign. That's a part 2. So that's what I would recommend, is timesing this equation by 2, leaving this one alone. So it makes that negative 4x, 18y, and 62. I just doubled each number, and then I can add, and the x's cancel out. That's 23y equals 69. Divide by 23, and you've got your y solution of positive 3. Then you need its x counterpart. Again, you go back up to one of your former equations, any former equation. To get that, you'll have to solve a little bit. Let's say I use this equation. 9 times y, I know now to be 3, equals 31 plus 2x. And then solve that for x. 2x equals negative 4. So x is negative 2. Your solution, x is negative 2, when y is 3, should be the one true solution for these two original equations when checked. Let's move to an example now where you'll have to manipulate. We'll call this manipulation whenever we're changing our equations around to get our goal. We're manipulating the equations, not changing their value, just working with them, manipulating. So let's say we have these two equations. If I add straight down, nothing cancels out, so I can't do that. But I also don't have the luxury of only timesing one equation by something that makes it 3. Like, what can you times 2 by that makes it 3? Nothing nice. You can times it by a fraction. What can you times 3 by that makes it 2? You can't make those match up easily, you know. So what I'm going to have to do is do something to both equations. And what's in the back of my mind, really at the heart of this, is LCDs. I'm trying to find the least thing that I can make 2 and 3 both look like, which is what? 6. 6 is that number in your mind. You're trying to make both of those 6s. And you can do it from the y's or from the x's. It's whichever one you want to focus on. At least they already have different signs, so I won't have to worry about making the sign change. So if I times this equation by 3, that'll make that a 6. Then I'll have to times this equation by 2 to make it a negative 6. And that's fine as long as I do it through the same equation. So tripling each term is fine. Doubling each term in the one below it. And now when I add the equations together, that drops out like we had planned it to. And I made this up, so it doesn't come out nicely, but it is solvable. When I divide by 5, I do get a solution for y, 29 fifths. Then I would sub that in to one of the former equations to get its x counterpart. But I'll let that go at that time. But I just wanted you to see how you could manipulate both equations if needed. All right. Now I'd like to focus your attention back to the 3 types of solutions that you'll get. When you solve systems, if you get a solution, a point where they cross, we call that a consistent system. For example, these 2 equations, when graphed, do cross because they have different slopes. So they cross once if you have different slopes, and you could find that without graphing just by solving for y and comparing the 2 slopes. Inconsistent systems are parallel lines. So they have the same xy ratio. So if you would solve for y, you would see the mx plus b form, that the slopes are the same, but you have different constants, therefore making them unique lines. So parallel lines have the same slope and therefore never cross, so no solution. The third possibility we said is a dependent system. That's where they're really just the same 2 lines. It's the same 2 lines. And sometimes you can't really tell it until you clean it up and rearrange the terms. But when it gets down to it, they're the same ratio of x to y, the same constant, just the same line. So if you graph it, it's a line on top of a line. And we call it a dependent system, and there'll be infinite solutions. And sometimes that's good enough. You can just say, oh, there's just infinite solutions. The question will be, how many solutions do you get? And that's good enough. Sometimes, though, the question asks you more specifically to name where those solutions lie. So name how you could call that line. So this is a more exact naming, and I saw in your homework you do have to do this on one problem. So for example, if it says to solve the equation and use x arbitrary. So obviously these are the same line. So the solution isn't just any x, y that I come off my head with, like the point 1 and 5 may not be on that line. You know, it may not be a solution. So it's not anything goes. But there is an infinite amount of things that do fall on that line. And how can you say what those points look like? You could call it the set of xy points. So this is the kind of fancier notation if needed. Little braces. Anytime we use braces, that means we're talking about the set of something. Then the xy coordinates. So the set of xy coordinates such that, or following this rule, that you have x in the x coordinate spot, and then name the y coordinate. Now the reason I did this is because it said to use x arbitrary. So that means make x the variable that we're working around. So in the x spot we call it x. Then for y, we're not just going to say any old y. More specifically, the y value will be the y that solves one of these equations. They're the same, so it doesn't matter, whichever one. 2x plus 3y equals 4. Solve it for what y would be. So solving for y would be throw the 2x across the line, divide by the 3, and y would look like, algebraically, negative 2x plus 4 over 3. So that's what I put in the y spot. That's how we do x arbitrary. X is the variable we're solving it in terms of. All right, so when you see that in your homework, I want you to be familiar with that. All right, then the last thing on this section is 3 variable equations. So if you'll flip the page, how much time do you have?
Maybe 4 minutes.
That's what I need. All right, so next page, what if you have 3 variables and 3 equations? So let's go with the example on the next page. 3 variables, so an x, y, and a z in this case. If you have 3 unknowns, it takes 3 equations to solve that. And I always like to think of a Walmart example. If I just said, my husband went to Walmart and he bought 3 things and they added up to be $4. I really don't have enough information to tell you what each item cost. If he has or let's say $2. He has item X plus item Y plus item Z, and it added up to be $2. If I said, how much did each item cost? There's an infinite amount of ways that can happen. 50 cents, 50 cents, and $1, 25, 25, $1.50, on and on. I could go forever with different ways to add up 3 things to get $2. Even if he gave me a second clue and said item X and Y were the same price, but item Z was double that, it could have been still a lot of things. Without belaboring the point, there's still an infinite amount of solutions to that. But if you get 3 clues, then you can nail it down. So 3 unknowns takes 3 clues. And that's what we have in a 3 variable equation. We have 3 unknowns, 3 clues, or 3 equations to solve by. So what we do is we label those 1, 2, and 3, and then we go through the set of steps you can see listed here. The first step is to kind of whittle this thing down into 2 variable equations and do what we just did on our previous problems. So how do we do that? We pick a variable, whichever variable looks easiest to deal with. Like, first off, my eyes see the z and minus z, that I could add these 2 equations together and z would drop out. So I pick a variable I want to eliminate from 2 different combos. So 2 plus 3 would be 2x and 1x is 3x, y and y is 2y, and the z's dropping out equals 4. So that creates a new equation, and I'll call that, and you can see in the notes, we call that equation 4. A new equation we created by adding 2 and 3 together. Then I want to create another equation with the same 2 variables. I want to eliminate z from a different combo, either 1 plus 2 or 1 plus 3. A different combination where I eliminate z. So let me follow my notes. I did equation 4 and 5. Oh, wait a minute. What did I do? Equation 2 and 1. Sorry. I did 1 and 2 together. I took equation 2 times 6 because it wouldn't naturally add out unless I did a 6 there. So I multiplied equation 2 times 6 and then left equation 1 alone. So equation 1 didn't need anything done to it to get the z's to drop out if this one is times by 6. Now when I add those 2 equations together, the z's drop out again. And I'll call that equation 5. That is really the new part of this. If you can get 2 equations with the same 2 variables, look at equation 4 and 5 compared. And you're really back to where you started on my earlier problem. Now you have 2 equations with x's and y's, the same 2 variables, and you can either add those or use substitution or get the solution to that system, and then you'll have a solution. You'll have at least a start to the solution. In my notes, you may have noticed that it would be